Welcome to the fifth video in the relativity topic. In this video we'll start to look at some of the more challenging ideas of relativity. So we saw in the last video that Einstein's theory of special relativity manages to successfully explain both Newton's laws and Maxwell's laws, and it's based on the two rules, that the laws of physics are the same in all reference frames and that the speed of light in a vacuum is constant. So disregarding Newtonian mechanics or Newtonian physics and starting from these two postulates, Einstein developed a theory that describes the mechanics, as it were, of the universe, and his theory encompasses all possible speeds that we know of. So it encompasses things not moving, so stationary objects, right up until things moving at the speed of light. Whereas Newtonian physics can only deal with things moving at very slow speeds. So the interesting question to ask is why? So what part of Newtonian physics is the limitation? And so to answer that question, we need to look at what assumptions that we make, or what assumptions that Newtonian physics makes. And these assumptions are so fundamental that we don't even think of them as assumptions. But what we do is that we assume two things. We assume that time and space are absolute, and we assume that they're independent. And what that means is we assume that the rate at which time passes doesn't change, and also that the distance that we call a meter doesn't change. So in this video, we'll start to look at the first of those assumptions, which is that time is absolute. So the rate that time passes doesn't depend on anything. And to do that, we'll look at our friendly little rocket. So we have our rocket, which is travelling with some velocity v relative to the space garage. For convenience, we will take the length of the rocket to be equal exactly to the length of the space garage. And also for my convenience, we will take this lovely picture and replace it with a red square. On the spaceship, there's a clock, and that clock is a light clock. So how a light clock works is that a beam of light sent out from the bottom of the ship, in this case, travels across the width of the ship and is reflected back to its starting point. 1 second is the time it takes for the light to make that round trip. And so what we're going to look at is what the astronaut and what the space mechanic see the light do from their points of view, so from their individual reference frames. And we'll start with the astronaut. So in her reference frame, the space garage is moving to the left and she's stationary. So she's travelling with the light. So the light has no velocity in the x direction relative to her, and she sees the light go straight across the cabin and come back. And so we will call the time it takes the light to go across the cabin in one direction the time interval delta t dash. And so 1 second for the astronaut is therefore the time it takes the light to go there and back, so 2 times delta t dash. From the point of the space mechanic, the ship is travelling to the right with a velocity v. So he will see the light travel diagonally. He'll see the light move vertically across the cabin, but at the same time, that cabin is travelling relative to him with a velocity of v to the right. So we also know for him, in his case, that the time taken for the light to go out and come back is the same, and we'll call this interval delta t. So for him, 1 second is equal to 2 times delta t. Our next step is to relate delta t and delta t dash. So we'll start with the astronaut. From her point of view, the light moves across the cabin, so the distance the light travels on one pass is the speed of light times the time it travels for. So that is c times delta t dash. In the case of the mechanic, we need to use a little bit of Pythagoras. So we know that the distance the light travels is equal to the speed times the time. So in his reference frame, that's c times delta t. We also know that the vertical distance that light must have travelled is equal to the distance across the cabin, which is c times delta t dash. And we know those distances are the same in both reference frames because there's no relative velocity in the vertical direction. And the other thing we know is that in the time it takes the light to travel once across the width of the cabin, the spaceship has moved a certain horizontal distance, which is equal to the speed of the spaceship times that time. So that's v times delta t. So now we have our right-angled triangle, and we can use Pythagoras. So we can see that the distance the light travels, the total distance squared, is equal to the y distance, or the width of the ship squared, plus the distance travelled in the x direction squared. So that gives us that c times delta t squared is equal to c times delta t dash squared plus v times delta t squared. And when we simplify and solve that formula, we can see that delta t dash is equal to delta t times the square root of 1 minus v squared on c squared. And since we know that v is always less than c, that means that that square root term, 1 minus v squared on c squared, is always less than 1. So what that means is that that time interval that passes in the rocket, as seen from the space garage, is longer. That is, it takes, in the time 1 second passes in the space garage, less than 1 second has passed on the rocket ship. So time takes longer to pass for things travelling at relativistic velocities. And this is the phenomenon called time dilation. That also leaves us with a small problem, in that now, since our time is also relative, we have no fixed interval that we can define as 1 second. And so we get around that by defining something called the proper time, or the proper time interval. And that is the time interval measured in the reference frame at which the clock is at rest.